Hi everyone, this is Compression Art and this is episode 2. On episode first we talked about Huffman tables and how to create them. What is less talked about Huffman tables and Huffman compression is how we actually send them over to the compression side. So the sender has to create a Huffman table, and so if we actually assume there is a compression over here, a Huffman table or tree is created. It has to be sent across with all the data that's compressed to the other side, so the other side can decompress the data. And not many people talk about this in the literature. So let's look at the Huffman table that we had last time. So this was the phenomena we talked about. Phenomena A happens with 85%. The three other phenomena happen with 5% probability. And we created something like this for it. But if you think about this a little bit, you realize, okay, the only thing that has an influence on the expected length or the average length of the Huffman tree is only the length of the branches. And if somehow this structure will be converted to this structure, it doesn't matter, because over here A has the same length as A here, B has the same length as B here, C and D have the same length as each other here. In other words, if I list all the features of these two trees, the only thing that matters in the expected length when we calculate it is the length of representation of each of the symbols. And it doesn't matter whether this is this one or whether this is this one. So what they do is, when they are sending this over, is that they assume that every branch on the right is longer than every branch on the left. Then they can somehow encode this a lot easier than this, because in this case you have to first know, actually you have to send each of these, and then you have to send each of these encodings. But if you do this here, you can do it with a trick. So what they do, this is the expected length of both Huffmans that we talked about. They are the same. The right form is also called the canonical form. And there is another point in using it, is it's easier to decode as well as it's easier to represent. So let's go on how we are gonna represent this. So very common way of representing this kind of tree is you count the number of the code words that have a specific length. So you count the number of code words that have length 1, there is 1 in here, length 2, there is 1 in here, and length 3, there is 2. And you also have to say what labels are there. So when these numbers are sent to the receiver says, okay, I have to create a tree. Okay, there can't be no length 0. When I create length 1, okay, I see that there is one length 1. So I keep this as a terminal node. I expand the others. I see that there is one length 1. I terminate this. I expand the others. And there is two lengths 3. I terminate these and nothing is left. So I can create this with these numbers. The only thing that's left is the labels, and they can be sent over the channel without complications. This representation is used in JPEG files, actually the JFIF JPEG file format file, and they have representation for a Huffman tree with 162 symbols and the maximum depth of 16. So their maximum depth of the tree is 16. And the labels are, for our example, the labels are sent in this sequence. So A, B, C, and D. So from left to right, at each level, you're gonna write down all the labels one after each other, and you can send them as a sequence. All right, let's see how much space does it need, because it's about compression. Everything is about compression. In this representation, for these numbers, we see that we have to send this number that many times. So we have to at most send maximum depth numbers, which is, in case of JPEG, this is 16. This is maximum depth. And we have to tell the receiver how many symbols are in that length. And it can possibly be, all the symbols can be on the same length. So all the symbols can be on length like 8, and it will be like, so it's for representing this, we have to represent between 0 and the total number of zeros, which for binary representation we have to use log of that many symbols. So in total, that's the total number we get. So for 162, they round up this to 8 bits, which is 1 byte, so 16 bytes here. And for representing the labels, we have to send each label once, and each label takes logarithm of number of symbols, 162 times 1 byte each symbol. So it's around, let's say around 180 bytes in JPEG. That's not that much of a space for sending a JPEG file. All right, now here we can talk about this in a more complex situation, since we went over basics, how we are gonna send it something that's much more complicated like this. The same principle holds. For length, for depth, for length 1, there is no branches here. For length 2, there is 2 branches. For length 3, there are 3 branches. For length 4, 0 branches. For length 5, 1 branch actually. For length 6, 5 branches, and for length 7, 2 branches. I can reconstruct this easily in the same manner. For length 1, we have no branch, so nothing is ended. For length 2, 2 are ended, the others are expanded. For length 3, 3 are ended. For length 4, 0. For length 5, 1. For length 6, 5, this, and this. And for length 7, 2. Okay, these 2. Now somebody can say, okay, can we do better? There is another representation actually, and it's used in zip format files, because zip also uses Huffman. All right, in the current format, in the JPEG format that we talked about, you can see that both these trees are possible, since you are sending labels independent of the structure. You're sending the structure in one sequence, and you're sending the labels in the other sequence. You can see that, okay, I can prefer one of these and make sure that already happens, and I can encode one of them. It assumes on each level the symbols are ordered. Then, based on these information, if I know how long is the length of each symbol, then I know on which level each symbol is, right? So if I know on which level each symbol is, I can associate it on using this assumption that we added, that each level is sorted. So if we have this, which is the length of each symbol, then I can say, okay, first I have to convert this to the JPEG format. I see there is one length 1, one length 2, two length 3, and I can create the structure. Then for labeling, I see, okay, for length 1 there is only A, for length 2 there is only B, for length 3 there is only C and D. But for C and D, because I don't want to confuse myself, always C comes before D because it's alphabetically less than that. All right, let's see how much bits does it need, how much information should we send for this kind of representation. You see that for representing each of these numbers, we have to use logarithm of maximum depth, and we have to repeat it for each symbol. And on total, this is not that much. If I do the same thing for JPEG, if I could do this for JPEG, but in the standard it's not possible, you would get 16, and log of 16 is 4, and this would be half the size of, almost less than half the size of what you get. So this is half a byte, that would be 81 bytes. All right. These are the two representations that are actually used in Huffman compression, and how you send the table to the receiver. Next time we are going to talk about how using the canonical form, this form, that the branches on the right are always longer, how it will affect the decoding process of Huffman codes, and how we can speed up decoding based on knowing that this structure holds. And since we know that this structure is the right structure, we have this representation available to us, and we don't have to have a big data structure representing the structure, and we can do things much more efficiently for decoding. But in representation, this is all we have to know. All right, I will see you guys next time.